So this is your video for today, Chapter 3, Section 1, Forces and Newton's Laws. We're going to be talking about the force of gravity. I will do the 3 problems on page 78. I will cover the questions 4 through 8 on page 79, and then I would ask you to do page 78, numbers 9 and 10. So have a pen and paper and maybe a calculator ready for that. You need to practice this. In this section, we're going to be working with this formula that the weight is equal to the mass of an object times the gravity or the acceleration due to gravity. Now here on Earth, the acceleration due to gravity is equal to 9.8 meters per second. We expect you to know that here on Earth. We really do. And so the formula turns into this triangle: mass times the acceleration is equal to the force, and that is going to be in newtons. Mass is going to be in kilograms. Acceleration is meters per second. So here is our set of questions that I will be solving for you. A squirrel has a mass of 0.5 kilograms. What is its weight? Now its weight is going to be in newtons. We're assuming the squirrel is here on Earth, so we have to know what its acceleration due to gravity is going to be. Question number 2. Again, the boy is on Earth. The boy has a weight of 400 newtons. We know he's on Earth, so we know the acceleration. So what is his mass? And question number 3. An astronaut has a mass of 100 kilograms and has a weight of 370 newtons on Mars. So we know it's not 9.8 meters per second squared. We're going to find the new acceleration on Mars. Okay, so the squirrel has a mass of 0.5 kilograms. What is its weight? So we need to find the force due to gravity. That's what we want to know. We know that according to this formula, if we cover up the force, we know we need to know the mass times the acceleration. So now we know what the formula is going to be. Mass times acceleration. So now we need to figure out what is the mass. When we read the problem, the mass is 0.5 kilograms, and the acceleration due to gravity here on Earth is 9.8 meters per second squared. So we're going to take 0.5, that's half, times 9.8. So that is going to be 4.9 kilograms meters per second squared. In this set of units, we've talked about this already in previous videos, that is equal to a newton. So this is 4.9 newtons. So number 2. So again, we have a boy, weighs 400 newtons. What is his mass? We assume that this boy is on Earth. So again, what is its mass? We're trying to find the mass. We know that we're going to use this formula. Pardon me. We know we have this triangle. If we cover up the M, we know the F is divided by the A. So mass is equal to the force divided by the acceleration. What is the force? The force is 400 newtons. The acceleration is, again, here on Earth, 9.8 meters per second squared. If we do the math, 400 divided by 9.8 is 4.1. 400 divided by 10, if we rounded this off to 10, it would be 40. We'll do that with a calculator. It's going to round off to about 41, and the mass is going to be in kilograms. Why is this in kilograms? Because what is newtons? A newton is equal to what? This whole newton thing is equal to what? It's a kilogram meters per second squared. Well, this part cancels out. The kilogram is left over. Or you can just memorize that mass is always just reported in kilograms. So this is your answer. Problem number 3, page 78. An astronaut has a mass of 100 kilograms and has a weight of 370 newtons on Mars. What is the gravitational strength of Mars? So we want to know the acceleration. Force is equal to mass times the acceleration. Divide both sides by mass, or we can use our triangle. We're trying to find acceleration, so acceleration is equal to what? Force divided by the mass. The problem tells us that the force is 370 newtons and that the mass is, what did it say, 100 kilograms. So we do the math, 370 divided by 100, pretty easy. So this is 3.7. This is equal to 3.7. Now what is acceleration going to be in? It's going to be in meters per second squared. Why does this work again? Because a Newton is equal to what? What is this Newton equal to? This Newton is equal to kilograms meters per second squared. That means the kilograms cancels out and you're left over with the meters per second squared. Makes sense because acceleration is in meters per second squared. 370 divided by 100 is 3.7. Okay, page 79, if you're following along, if you're looking at your book, it says describe 2 forces that would change the motion of a bicycle traveling along a road. You could have it speeding up or slowing down. Well, how would you slow down a bicycle? Probably some type of friction. We're going to say we're going to apply force to the brakes, and the friction of the brakes is going to slow that down. To speed it up, you would probably say that there is some type of force being put into it, into the gear mechanism. So pedaling harder would cause it to speed up. Number 5. Can there be forces acting on an object if the object is at rest? Yes. Here's the reason why. If there is a wall right here and you are pushing on it, are you putting a force into that wall? Yes, you are. Is the wall moving? No. Why? Because it has an unbalanced force of the strength of that wall is pushing back with however many newtons that you are pushing in with that many newtons. So that can be at rest. The next part of the question is, must there be an unbalanced force acting on a moving object? So let's say we've got Earth and the moon, and there is some type of object flying away from the Earth and the moon through space. Okay, let's say it's some type of satellite. What happens if that thing is traveling at so many thousand miles per hour, but it's traveling in a straight line at a constant speed? If there is no gravity, if it's far away enough from the other objects and there's no gravity, it can be moving at a constant speed with no air friction, air resistance, or anything like that. So, yes, it can be moving at a constant speed with no unbalanced forces on it. So if you get into astronomy and astrophysics, you're still going to have gravity, though. Number 6. Why does coating surfaces with oil reduce friction between the surfaces? So if things are touching, remember in this chapter, if you have this object resting on this other object, at a microscopic level, there's these things called micro welds. And in chemistry, we get into intermolecular forces where these things are actually close enough and if they're not moving, they will actually form these little forces called micro welds. But if we put a coating of oil in between these things, this liquid layer actually does not allow those things to get close enough, and so it acts as a lubricant. That's why we have these things in engines, in your gears, in your transmissions and things like that, to reduce this ability for these objects to come into contact with one another. They do come in contact with the liquid, but that doesn't have nearly as many strong forces as the micro welds themselves, and so it reduces that friction and reduces the heat and keeps things running smoother, longer. Question number 7. Distinguish between the mass of an object and the object's weight. So let's say this is you. Hey, this is you. Okay, we'll put some pants on you, okay? And maybe a shirt. Okay, this is you. However much material is in your body is your mass. Now, if we put you in an astronaut suit, that suit is going to have mass as well. Whether you're here on Earth, you have the gravity at 9.8 meters per second squared. That is your weight here on Earth. But if we take you to Mars, in the same astronaut suit, you still have the same mass. You're still made up of the same material. Your spacesuit is still made up of the same material. But on Mars, it's only going to pull down at 3.7 meters per second squared. So your weight will be less on Mars. Your mass will be the same on Earth or Mars. The mass is the amount of material. Question number 8. Suppose that Earth's mass increased, but the diameter did not change. How would gravitational strength near the Earth's surface change? Gravity is based on mass and distance. So if the distance stayed the same from the center of the Earth, that means it didn't get bigger, but its mass increased. The mass increases the gravity. So guess what? The gravity would increase. So if you would, using what I did on questions of number 1, 2, and 3, you calculate the answers to number 9, calculate weight on Earth. What is the weight of a large screen TV that has a mass of 75 kilograms? So you are looking for the force for the weight. That's going to be in newtons. So you need to be able to do that for number 9. For number 10, calculate the net force. 2 students push on a box in the same direction. One student pushes in the opposite direction. What is the net force on the box if each student pushes with a net force of 50 newtons? So here's the box. It's a big giant box. You got this one student pushing this way, and you got 2 students and they're all 3 pushing with the same amount of force. So however many newtons, and this person is pushing back with the same amount of newtons, okay? What is the overall force, unbalanced force on this box? So there you go.